because of time schedule that we are going to start, and to begin with, we introduce the juror. Our juror is Professor Liu Xiangning from National Taiwan Normal University, and Professor Gao Chongwu from Zhongyuan University, and Professor Xu Mizhi from Zhongxin University, and Professor Gao Danmi from Qingdong University. Okay, let's begin with the reporter. So the reporter, the leader of the reporter, could you introduce your team members to?
Hello everyone, I'm Xie Chenhan, and the team captain from National Experimental High School. And this is Duan Yiming, Liu Shanglou, Dai Yunjie, Dai Yichen. Thank you.
Okay, and then the opponent, the leader of the opponent.
We are Chen Hongho, and this is Wu, this is Li Zhongwei, this is Chen Hong, this is Dan Hongwei.
Okay, and the reviewer.
Hello, honorable jury and fellow competitors. Team is Xiaobian, and I'm the team captain Liu Yushen. And these are my teammates, Li Kunxian, Zhong Jian, and Yu Rui Chen.
Okay, so I think that you probably should have be familiar with the 5 schedules and the 5 regulations, but I will announce again for the regulations and the time schedules. So the first section of the first stage of this is the opponent trying to report it for a problem in 1 minute, and then the reporter accepts or rejects the challenge in 1 minute. And then the third stage is the preparation of the reporter in 5 minutes, and the presentation of the reporter in 12 minutes. Questions of the opponent to the reporters and answers of the reporters in 2 minutes, and the preparation of the opponent in 3 minutes. And the opponent would take the floor in maximum 4 minutes, and discussion between the reporters and opponents in 14 minutes. And the opponent summarizes the discussion in 1 minute, and the question of the reviewer to the reporter and the opponent, and answers to the question in 3 minutes. Preparation of the reviewer in 2 minutes. The reviewer takes the floor in 4 minutes, and concluding remarks of reporters in 2 minutes. Questions of the juries in 5 minutes. And so the system would start the counting of the time after I say start going to the next stage. So let's go to the first stage, and the opponent, you have 1 minute to challenge the reporter. Let's count, go to
I want to challenge question 12.
Problem 12. So the reporter, you have 1 minute to decide.
We would like to accept the challenge.
Okay, so the reporter accept the challenge for the problem type strange motion. Okay, so we go to the next stage. Okay, and then so the leader says you someone to write down the name of the representative. So I think that due to the CDC regulations, so indoors we should have the mask on. So all the three teams, so that I think that is fair.
When the captain attends the meeting in the first day, the person in front tells us that when you are reporting, you can take your mask off.
But I think that
the
CDC has the final decision. Yeah, I think it's basically that we take. We put the mask on. Yeah. But I think that the CDC have regulations, so it's above all our regulations, so we cannot exclude the CDC review. And it's fair because in all three teams we value your relative performance. So okay.
So I would like to start my presentation.
Okay. So our reporter have 12 minutes to present. So let's go to the next page.
Hello. honorable judges, and fellow contestants. Today, I'm Darren Jie from Team Me, and today I'll be presenting question number 12, strange motion to you. So let's start with the outline. So first we'll go into the problem statement where we get to kind of know what we're looking for. And then next we'll see an observation video. And then we'll go into our theory part where we explain the phenomenon. And then we'll do some experiments on different parameters. And then we'll finally reach a conclusion. Okay, so now moving in. The problem statement is that we should sprinkle a small floating particles on the surface of water in a bowl. Bring a strong magnet above and near to the water surface. Explain any observed motion of the particles. So the first thing that we'll have to take a look on is that we should use small floating particles, and then we should put it on the surface of water. So we think that small floating particles and waters are essential in this particular question. So we bring a strong magnet, which we suppose is about magnetic field, and then we're supposed to observe the motion of the particles. So continuing to the observation video. So as you can see right here, when we're using paprika and sprinkle it on water, while we're moving the magnet, it's supposed to come inside, come near the magnet, and then follow it. So it follows the direction of how the magnets move. So then let's start explaining the phenomenon. So first, we'll talk about diamagnetism. It is a very weak form of magnetism that is induced by a change in the orbital motion of electrons due to an applied magnetic field. So usually we know that our particles are usually separated into either ferromagnetic or not ferromagnetic. And in that case, when we're talking about non-ferromagnetic particles, we can also separate it into paramagnetic particles and diamagnetic particles, which they would all show their characteristics only when an applied magnetic field is added to the system. So moving on, a diamagnetic substance is one of whose atoms have no permanent magnetic dipole moment. So it is also the atoms of it repel magnetic fields. And whenever two electrons are paired together in an orbit, so we all know that the m of the electrons should either be positive 1 out of 2 or negative 1 out of 2. And when we pair them together, their total spin is 0. So that's when we call them diamagnetic electrons. Okay, so now moving into the Paul-Leven's theory, this is where we describe the diamagnetic susceptibility of a magnetism substance. So a magnetic susceptibility is used to describe if a substance is either diamagnetic or paramagnetic. When it's smaller, when this pi right here is smaller than 0, then we call the substance diamagnetic. However, when it's bigger than 0, we call it a paramagnetic substance. So if we take usually a magnetic susceptibility is written as mu0 times at the end right here, and then also times the magnetic moment divided by the applied magnetic field. So so after we put it into the Paul-Leven's theory, it will look like this. And where the r squared means mean square distance of the electrons, and where the E represents the charge of electrons and represents the mass of electrons, and then the Z is the number of electrons of an atom, and then N is the number of atoms per unit volume, and where mu0 is the permeability of vacuum, which is 4 pi times 10 to the negative 7 degree. And then so if we take a look at all of these constants, we can find that this should be positive, this should also be positive, and all of it are supposed to be positive as they all represent either mass or numbers or this one, which is also positive. And then also when we square them, the charge of electrons should also be positive too. So by multiplying several constants with positive, we should get a positive pi. However, we put a negative sign right here, so which makes the whole thing negative. So we can say that this is supposed to describe the diamagnetic susceptibility of a diamagnetism substance. Okay, so so we all know, so according to the internet, water is a diamagnetic material, and where we see that its diamagnetic susceptibility is minus 9.1. And then so, however, the interaction of water and magnets, they're actually really small. So what we're trying to do right here would be to, what we're going to do later is that we would see how we can actually observe the diamagnetism of water. And so usually visually notable effects can only be obtained using powerful magnets. So that's what we also try to do. So if we see right here in this video, when we put like straight lines which would reflect onto the water surface, which is a still water surface. And then so in that case, when we put a magnet closer to it, we can see like the wobbling of the lines, which we think represents a dips on the water surface. So if we were to put it in a picture, you can see that the line right here is not straight anymore, which so we think that it represents there's actually a dam on the surface of water. So in that case, why we think the particle moves is that when the magnets comes in, they create a small dam on right here, and then so the particles they move inside. The particles they move inside the little dam, and when the magnetic field is removed, they're not supposed to. So it floats back onto the flat surface, and so it stops moving. Okay, so for the experiment, so now that we know that it's the main cause of the movement is because of the diamagnetism of liquid. So we chose different parameters, including like different kinds of particles, and used different kinds of liquid. So for the experiment, like different kinds of particles, we used different kinds of particles such as paprika and chalk, and then the particles all float on the surface of the water, which fits the problem statement. In that case, when we use water plus paprika, just like we see before in the observation video, it follows in the direction of how the magnets move. And then when we use chalk, the yellow chalk dust right here also follows in the direction of the magnet's move. So in comparison, we can see that different particles hardly affect whether the particles move or not, unless, but there's an exception, unless it's a ferromagnetic particles, because in ferromagnetic particles, if it's a ferromagnetic particles, we suppose that it's supposedly to just line up like the magnetic lines, magnetic field lines. Just like when we spread up the ferrite powders on the tables, when we put in magnets close, it would form like how the magnet's field would shape. So we suppose that if we use a ferromagnetic particles, it would also look like that. Okay, so now moving on into the next parameters that we chose, different kinds of liquid. So the liquid that we used were water and canola oil, and we used paprika as a small floating particles. So we all know that water is a diamagnetic substance. However, the canola oil, according to the internet, usually most organic substances are also diamagnetic substance. However, we think that the magnetic susceptibility of canola oil is actually a lot smaller than water. So moving on into the experiment, it's just like we see. So we keep the particles same this time, and then so it's still, when we use water, it's just like follows it. Okay, but when we use canola oil, we can see right here that the particles, though it's not very clear, but the particles, they hardly move, and it doesn't follow in the direction of the magnet's move. So in comparison, we use the same method that we chose to see if water actually has diamagnetism. We also did this to the canola oil that we used. So if we can see it right here, there's a curve. However, there's no curve right here, so we suppose that the effect of the diamagnetism of the canola oil is either too small or there's not even a bit. So in discussion, we reached a conclusion that canola oil either doesn't have diamagnetism or that its diamagnetic susceptibility is too small for us to observe anything. So therefore, the particles on the surface of oil won't follow in the direction of the small magnets. Okay, so in conclusion, particles move because of the diamagnetism of the water, which it creates a dam right here, which also acts like a gravitational field, which pulls all the particles in and then make it move when we make it follow the direction that we move it when we also when we move the magnets. And the other is that water's dynamic, so that's for the second point. And then different particles do not affect whether the particles move or not, because we think that it's the main cause of the motion is actually the diamagnetism of the liquid that we're trying to use. And so unless they're ferromagnetics, just like I explained before, which we suppose that it's supposed to line up like the magnetic field. And then the last point, when using canola oil, there's no motion on the surface of oil. So just like we explained, we suppose that it's because its diamagnetism is either too small or that there's actually none. So for future experiment, we can try to change the strength of magnetic field, because the problem statement actually asks us to use a strong magnet. So we did try to use like the strongest magnets we find, but however, it was not able for us to control like how strong the magnetic field is. We also tried using like electromagnets in order to try to control the magnetic field. However, the change in the magnetic field was too small and then hardly made any impact. We also used like Vernier magnetic field detector from Vernier to try to measure how the magnetic field looks like. However, it was still just like by using different magnets or just using electromagnets, they were all really difficult for us to see the difference in the magnetic fields, and therefore we could not conduct the experiment, and we're still looking for a way in order to achieve that. And that will be the end of my presentation. Thank you.
Okay, so the opponent, you have 2 minutes to question the report.
First question, have you analyzed the direction of the forces?
You mean?
Sorry, I mean if you put magnets on it, so there must a force that drive them to move. So have you analyzed the direction of all the forces that the particle get?
Yeah. Okay. Yeah.
Could you draw on the blackboard?
You sure you want?
Oh, no, nothing. No, sorry. And the second question is, why did you choose canola oil?
Well, because firstly, we think that its diamagnetic susceptibility is much smaller than water, and then the second is that it's a easier substance for us and not very dangerous. We also tried to use like benzene, but it was kind of harmful to human body, so our teacher wouldn't let us use it.
So your purpose to use this oil is to prove that magnetism is the main reason that it moves. Yes, more.
Yes, in particular the diamagnetism of the liquid.
Okay. And why you use paprika? Why you use paprika to move? Because I think there are many kinds of particles that you can get.
So first, we have to neglect the powder that is actually ferromagnetic, and then the second, it has to float on the surface of water, and the third, it should not be solutable to water because we think that it might affect how the motion goes. So paprika, I think, fits all of these three conditions. That's why we chose it.
Next question: have you tried to measure the mass of the particles?
I would say it's kind of hard to do, so we kind of like use our eyes to see
Okay,
the
time is up.
difference.
Thanks.
Okay, let's go to the next question. The opponent has 3 minutes to prepare. Okay, time is up. So the opponent and the reporter, you have 40 minutes, and so the opponent have the first 4 minutes.
Sorry. So now I'm going to make our opponent report. Okay. The problem state is we sprinkle small floating particles on the surface of water in a bowl, and when you bring a strong magnet on it, near to the water surface, it will move. So the main focus is what motion that you can see and why did it happen. Next page. Oh, okay, the summary. It's the summary of their theory. They say when electron spin equals to 0 cause the diamagnetism, and they use Paul Langevin theory to describing the diamagnetism, and they say water is a diamagnetic material, so it will have a dam on it, and when magnet get close to it, will cause this phenomenon. It's the summary of their experience. They say different kinds of particles don't affect, and they also say that when they use oil, the effect is not very obvious that you can observe. And its conclusion: particles move because the magnetism of water. And when using canola oil, there is no motion on the surface of oil. So here is the suggestion. The advantage is that they speak fluently, but the suggestion is they have no quantification, so that when they try to explain this phenomenon, there's no any data to explain that their theory is true. And also, they didn't measure the major of the particles. So I think it's there for their suggestions. And so, and I want to show here. They use different kinds of particles, but after I heard their report, I think the particles they use are always diamagnetic materials. That means they never use like iron or other things that were attracted by the magnet. So I think it's one of their problems. So, and here is my report.
Okay. So then we start the discussion.
Okay, so the question now, I want to discuss that. The question 1, you just say you use different kinds of particles. So why don't you use a kind of like you can choose something that you can show you can show that every particle is the same. Like you can use small balls or anything that can make you report what. Also, why do you choose like petrocard, these kinds of materials that you can you cannot quantify it.
I'm sorry, but I hardly understand how you're supposed to quantify the motion. Because what we're trying to do right here is actually just observe the motion, and I'm not sure by quantifying what you mean.
Because if you want to explain this motion, I think you need more parameters.
Yeah, I agree that we can have more parameters. So like I said in this page, we can maybe do the strength of the magnetic field, or maybe even, as you suggested in the report, use different masses or different sizes of particles. I think that's all conductible.
So how can you show that the particle don't affect when you, because you only try some kinds of particles and you say particles.
Okay, so what I'm trying to say right here is that by using different particles, we can all see the trend which particles move towards the direction which the magnet moves. That's the trend that we're talking about, because that's the motion that we assume at the first time.
My question is, have you observed the motion of the like you say these kinds of particles both in the same, but I think they have some difference.
I do agree that by different sizes or how the water or how they interact with the water surface, such as the water tension, or like how much friction they have according to the waters according to their characteristic, they may have like different different velocity or anything like that. But what we're trying to see right here is that it actually has motions.
The next question is, why do you choose oil? Because I think in the problem statement it says it's particles underwater.
Yeah. So we try to use like such as counter evidence in order to show that water is necessary in this particular experiment.
But I think whether the oil, the particles on the oil can move is may not influenced by the diamagnetism.
And why is that? What do you think then?
Because I think oil is it is meant. I think oil is not. Sorry,
I suppose that you're saying oil may have different characteristics with the water.
Because if you sprinkle particles on the oil, it's hard to move at first.
So do you mean like the viscosity of water in oil might change? Yeah, so I do agree with you that there might be some parameters which we change by using the liquids that we neglected. But still, what we're trying to do right here is just to provide a counter evidence which we can prove that not every liquid can have the motion right here.
Okay, and look at this video. So how do you define that move and did not move?
I think it's pretty obvious that these right here, you see they stay still. However, when these particles, when the magnets move, it kind of follows it around. Like when we turn it, it turns also. And when we move, and when we like put it this way, then it also follows it. That's the movie. That's the movement that we see right here.
Could you show me the page that you explain that the diamagnetism will the picture? Yeah, this. So what do you think? Can you play with this? So you say when the magnet put on it, it will get into the depth of the water, and in your picture, the particles, when you get the magnet out, so the particle will flow it
And stop moving.
and stop moving. But in your situation, you just move this magnet.
Yeah, but we didn't put it on the PowerPoint, but when we take the magnets away, it's actually just stays still. And we think that, because that's not motion, so we didn't put it on the PowerPoint.
And the next question is, when you see this picture, if you can, if the magnet put on it, if you can attract it, your magnet is not really put on it, because if you put the magnet right on the particle, it won't move. Yes.
Can you rephrase your question?
If you put the magnet on the particle, the particle won't move because it just.
Yeah. If this is a table, like this is a table right here, and I just put a particle right. If I just put a magnet right here, oh, I'm sorry. If I just put a magnet right here, and this is a table, then the particle won't move.
So yes. So when it moves, it means the particles is not really in the center of the depth. So have you considered the influence of the surface intention?
I'm not really clear what you're trying to ask.
If you put magnet on it and the particle moves, means the surface of water is not flat.
Yes.
So have you considered the surface intention will affect this particle?
I hardly believe, well, because even with the surface tension, there's actually still a damping here. So I believe that, because there's a dam right here. So when the magnet is right here, according to like the gravitational force of it, we think that it will have a force this way, which will make it kind of like slide down to the end. So we cannot be really sure if the motion is actually stopped at the end. And
so what caused this force?
This is gravitational force. Well, are you trying to ask why is there a dam right here?
You just write the gravitation, but I want to know that why it will going.
Okay, so the actual force acted upon the particle is actually just the gravitational pull, and why does the other force doesn't affect it? So basically, we have a magnet here and then the water here. So it kind of generates a magnetic field which goes this way, right? So in that case, we all know that diamagnetic substances have a
So my question is, you only write the gravity, but the force is going to this direction.
Yeah, so it kind of reaches to the center of the dam.
So why? Because you just draw.
Oh, this is like, so when this and this combined is the gravitational force. So this is actually just a direction of the magnetic, so this is actually just a direction of the force that is separated from here. It's on the ground.
And you didn't measure the velocity of the particle. Yes.
Yes.
So you think it won't influence the?
It might be influenced, but we're talking about motion, and then so we have qualitative results in motions. However, we do agree that maybe by examining the velocity of the particles, we can get like more quantitative results in the motion of the particle.
I have no question.
Okay. So the opponent, you have 1 minute to summarize the discussion. Next page.
So now I'm going to summarize the discussion. We discussed why they choose these types of particles and liquid, and they say that petrica is the most suitable particles that they could choose. Although they can show that every petrica is the same. And also, we discussed the forces that the particles get. and they say the gravity make the particles
Okay,
move
time
to the
is
center.
up. So the reviewer, you have 3 minutes to question.
Okay, question for a reporter. What is your connection between your theory and the experiment? Okay, for example, when we see we're trying to see a dam right here. So we also gave other evidence in order to show that this was part of our experiment where we show that there's actually a dam in water. Did you use diamagnetic or paramagnetic particles to see the difference between them? I believe that I'm not quite sure what the particles we used are, but I believe that they should be maybe. Yeah. Do you think the concentration of liquid could affect the motion of particles? We're only using water, and we're also using non-solutable particles, so I don't think there's any concentration change in that. So for the opponent, do you think the surface energy of water will affect the motion of particles?
I think so, because
Okay. For the reporter and the opponent, do you think the gravitational force of particles will make great influence to the movement of particles? Yes.
I think so.
Okay. For the reporter, as you mentioned in the report, you said that you use canola oil, which is a paramagnetic liquid, and the particles won't follow the magnet, right? Yes. I didn't say it's paramagnetic. I believe that it's actually a really, really weak diamagnetic substance in my knowledge. So did you grab the oil? If the reviewer thinks that the oil is a paramagnetic liquid, and did you observe any motion like the particles moving away from the magnet? No. Okay. For the reporter, can you predict what will happen if using other diamagnetic liquid, not water or oil? Well, I believe that they will also have the movement that which we show right here. But however, according to how their diamagnetism susceptibility, the rate might be different.
Okay, time is up. You have 2 minutes to prepare. you have 4 minutes to present.
Hello, honorable juries and fellow competitors. I'm the reviewer from Team Excelsior, and today I'm going to review problem number 12, strange motion. And the problem statement. Sprinkle small floating particles on the surface of water in a bowl. Bring a strong magnet above and near to the water surface. Explain any observed motion of the particles. And we are mainly focusing on what causes the motion of particles and how the relevant parameters influence the motion. And here's the reverse outline. She has a observation of the paprika sprinkles with the motion. And in the theory part, she talks about the dimagnetism of liquid. She has well explained the phenomenon, but it is not quantitative. And for the experiment part, she talks about different kinds of particles and different liquids. However, it didn't match the theory. And for the discussion, it talks about the canola oil has no dimagnetism, and she has no experiment data. And for the conclusion, is the reason why particle moves. And there's no concrete conclusion. And for the opponent's pros and cons, he points out the lacking of force analysis, but he has too many discussions on why they choose the oil. And he points out the missing of experiment data, but he didn't have an opinion about how to quantize the data. And he talks about the better method to quantify the motion. However, he failed to clarify the phenomenon. And for a discussion, the opponent asked, will different particles affect the result? And the reviewer answered the trajectory will always be the same. And the reviewer disagrees with the reporter, because different particles, like mass or the radius of the particles, will affect the result. And the density of the particles will also affect the result. And for a discussion about trapping position of the particles, the reporter says that it is the comparison to the opponent asks, as you mentioned in your report, why didn't it change when you change the oil? And the reviewer said, reviewer view is that the reporter didn't observe the motion well, and we believe that if the magnet is strong enough, it will affect the oil since it is also a dimagnetism liquid. And for the point list, the reviewer and for discussion, they failed to discuss the characteristic of the particle, which is the paramagnetic or diamagnetic particles, and the mass and the density of the particles. And for the measurement part, they missed to discuss the quantification of interface deformation, like the radius of the curvature and the speed of the particles, and also the transformation of energy. And the energy distribution of the liquid surface, which is the potential energy and the magnetic energy and the capillary energy. And also the trajectory analysis of the particles and the boundary condition of the magnitude of magnetic field and the limits of the particles, which is the mass and density, friction, and collision. Thank you.
Okay. The reporter, you have 2 minutes to conclude.
Okay, so I'll be concluding the discussion in the whole physics part today. So basically, so just for some clarification, so how do we quantify? So how do we quantify motion? We can quantify including like using try to use different parameters in order to track the velocity, and also in for future experiments, which we lack here. So that's what we omit, but we also do omit that we can improve the experiment. So particle size should be the same. So as we said, it's according to the gravitational force. So we actually believe that different sizes of particles should be should affect, and that actually can be seen in our observation video. And then why didn't we use other particles such as iron powder? So we believe that iron powder is ferromagnetic, so it will immediately align according to the magnetic field lines, and then so we're supposed that any motion, the motion that we suppose right here would appear on any surface, including water. So in this case, it's not really investigating the phenomenon, because that's because that's not what we're trying to do right here. And then also the surface tension on dam surface should have an impact on the motion of the particles is considered. So we think that the impact of our gravitational force is actually much bigger than surface tension, so it to be neglected. However, we agree that it might impact the result. And then also for some answers to the reviewer's questions, so we also believe that according to energy, only the potential energy should be considered, while magnetic energy and other energy are kind of too small compared to the potential energy that we have for the particles, so they can be neglected. And then also for the we do believe that oil is diamagnetic, but in this case, when we put them in the same kind of but when we put them in the same magnetic field, we believe that the diamagnetic susceptibility of water is much bigger than the oil. That's why we couldn't see any movements in the oil. And that is the end of my concluding remarks. Thank you.
Okay. So we have 5 minutes for jury questions.
So I have a question for 13. The experimental they showing the moving with the yellow color thing is the magnet showing the picture. So the yellow thing is too far away from the magnet. So do you think in this case a dam can induce the flow, the following of the yellow thing? The yellow color dye is pretty far away from the under of the magnet. Do you still think this is caused by the dam, or there should be something else?
Doing this part?
Yes, the yellow color floating thing is basically pretty far away from the.
Yeah, so because we see that in this picture, right, in the one with in this one particularly, we can see that the dam is actually really pretty big. It's actually bigger than the magnets. So even when it's like kind of this, even when it's here, we think that it will start moving towards inside. So it might not always be in the center, but because of the dam created here, even the more away particles may also move.
So you think it's not? How about the other question?
I believe that I agree with what the reporter said, and I believe that if the magnetic force is bigger, then the particle will start moving when it's even farther, because the surface of the water will be the depth of the water surface will be even more.
In my opinion, we cannot show that the chalk is diamagnetic materials or paramagnetic materials. If it's a paramagnetic material, so it's just attracted by the magnet.
Okay, so any other question? Okay, Professor Liu.
I have a question for the reporter. What is the magnitude of your applied magnetic field?
So for my so I think it's 0.48 around 0.48 millitesla. If what I remember was right.
0.4 millitesla.
I think that's what the Vernier magnetic field instrument told me.
Okay, thank you.
Okay. So any other question? Professor
Yes, I
Chen?
have one question. Do you think the floating particle floating is important? The moving of the floating particle, floating on the surface is a key issue.
Yeah, yeah. So because we can see that it's only the surface that has been curved. So if it's not floating on the surface and it's sinking below, it won't have any movements because it's the surface that is curving and it's attracted by this difference in height.
Then is the volume, not just the surface.
Yeah, sorry.
So about the other question.
So it would be with the recorder because it is the deformation of the surface that causes the moving of particles. So if the particles, the mass or the density is too big, then it sinks under the water. It won't have any motion.
I think I disagree. I disagree their theory because it's based on its magnetic material that you cannot attract it by the magnet. But if there's just some iron powder on the water, if you put the magnet on it, these particles will also move to the center of the magnet. Even if oil.
Okay, quick question for the reporter. How do you show is the dent or a hump?
Because we just observe the
It can be a hump.
it's
Okay.
not really clear in this graph.
How many times? So, Jury, please prepare your score. When it's ready, please raise your score. Okay, so let's show the score of the jury. Okay, so for the reporter, this is
Sorry.
77887. And then for the score of the opponent, okay, 66465. And for the score of the reviewer, 77687. Okay. So we have 10 minutes for the